Welcome to our video abstract. Quantum effects are everywhere, from lasers to semiconductors to superconductors to chemistry and biology. Similarly, the field of control is essential for most modern technology, for example regarding robotics, guidance systems, microcontrollers, and chemical engineering. Naturally, we would also like to extend control to nanoscale systems and quantum dynamics in atoms, molecules, and quantum devices. This can be done by engineering the Hamiltonian that governs the evolution of the system via the application of optimized external electromagnetic fields. There are many applications of quantum control. In this paper, we focus on the implementation of robust quantum gates, which, once realized, would pave the way to full-scale quantum computers. A major obstacle for the realization of robust quantum gates are uncontrollable interactions with the environment that lead to decoherence, eliminating a system's non-classical properties. There are different types of environment. In the Markovian regime, system-path correlations decay fast, so that the environment has effectively no memory of past interactions with the system. Many physical processes are of this nature, for example the spontaneous emission of photons and phonons or collisional dephasing in atomic vapors. On the other hand, if correlations between the system and path are significant on the timescale over which the system evolves, then the environment is non-Markovian. This is typically the case for small structured environments such as one or more system qubits surrounded by weakly coupled noise qubits, as found in solid-state systems. Both types of environment are important in practice, leading us to the key question we study in this paper.
How do the differences between these environments affect our ability to coherently control the dynamics? Specifically, we address the implementation of quantum gates in different environments using optimal control. Assuming fields with finite time resolution, we minimize gate errors using an iterative algorithm. In each iteration, the fields are updated for all times at once, as shown, using a quasi-Newton method with exact analytic gradients, which is more efficient than the popular Krotov method. The performance of the algorithm is analyzed in terms of the minimum gate errors attained and the convergence behavior. For simple problems, little variability is observed. For more challenging tasks, however, frequent trapping, long tails, and diminishing returns make sensible termination conditions and repeated runs essential. To quantify the likelihood of success of a typical run and the time required on average to find a suitable field, new notions of success rate and success speed are introduced. Density plots, as shown, are then utilized to study the effects of parameters such as gate operation times and initial fields on these performance indicators. We also consider how fields optimized in a closed system setting perform for open systems. In a non-Markovian case, the fields can be substantially improved by explicitly considering the environment, while almost no improvements are seen in the Markovian case. How do the controls work? In the non-Markovian case, Bloch-sphere trajectory plots show that the improved performance of the controls is mainly due to suppression of indirect noise qubit excitations that result when the closed system optimal fields are applied. However, certain imperfections such as field leakage can cause unwanted noise qubit excitations that render the controls completely ineffective. The effect can be mitigated by explicitly considering leakage in the optimization, but at the expense of substantially increased gate operation times and control complexity. As shown, this demonstrates that there are limits to control robustness and underscores the importance of system design and characterization for control.